All right. Hello, everyone. Can everyone hear me okay? Doing good? Perfect. I'm seeing some thumbs up. All right. So thank you, everyone, for joining. For those of you who were here last time, welcome back. For those of you who are new, welcome. I'm Sam Foster, an application scientist here at Axcend. And we are going to be doing this series called Understanding Capillary LC with the goal to describe the various differences of capillary scale versus some of the more traditional analytical or prep scale HPLC systems that are out there. Last time we were joined by Dr. James Grinius, and we gave a very broad overview of the field that's on the Extend website if you want to catch up. This week, we're going to be focusing primarily on solvent delivery systems and really the differences that come from shifting down to the lower flow rates associated with capillary scale. So as a little bit of an introduction, we're going to talk about why we need low flow solvent delivery and really, give a quick explanation as to what capillary scale is. We're then going to follow up with a number of different of the most common pumping types, and we're going to conclude with sort of use cases, pros and cons, and where each one shines and where they sort of struggle and need some work. So to get started, what is the difference between capillary and analytical scale? If you were at our last one, we talked in depth about this, but as a quick reminder, chromatographic scale is typically defined by the inner diameter of the column you're using. So analytical scale columns, typically you're between 4.6 and 1 millimeter of inner diameter. And those are typically run anywhere from 0.3 to 5 milliliters a minute. When you're shifting down to the capillary scale, you're looking at columns that are 0.5 millimeters in inner diameter or less. There is a nanoscale down, I think, at 75 micron and below inner diameter, which we're not going to get into today, but there's all sorts of different methods for that as well. But really, the big difference and the primary need for new pumping systems is that we shift our flow rates by an order of magnitude. We're shifting from milliliters a minute down to microliters a minute. And with those shifts, in order to get reproducible and usable chromatography, there is a need to use solvent delivery systems that are optimized for those lower flow rates. And so that's what we're going to be getting into today. Now, what are our options? So there are a ton of different pumping systems out there, but really the four most common are pneumatic-based pumps, electrokinetic pumps, piston pumps, and syringe pumps. And we're going to go through each of these. But before we do, I thought it would be a little bit interesting to see what everyone's experience was. And so I'm going to be putting a poll up here asking what everyone's most familiar pumping type is. And so if you don't mind answering, what do you all use? I'm curious to see. It's looking like a mix of piston-based pumps and syringe pumps. Syringe pumps seem to be losing by a slight margin, and piston pumps are sort of the most favored. That to me tracks, and we'll get into why. I'll leave it up for another couple of seconds. Perfect. I think we filtered in. So it looks like piston pumps are in the lead with 50%. We have syringe pumps in second at 35 and new to all of them at 15 with no responses for pneumatic or electrokinetic. And that is really interesting. We'll get into some of that a little bit later. So let's start with pneumatic-based pumping. There we go. So pneumatic pumps are probably the simplest of all of the pumps we're going to be talking about today. It's a piston-based pump in which you fill a reservoir or a piston, and then you apply gas pressure to the head of that pump in order to drive the solvent out of that piston and back into the system. This is a very simple way of doing it. It's very lacking in parts that can break. There's no motors, there's no drive shafts. So it's a very sort of rugged approach to it, but it does come with a number of caveats. So first and foremost, typically it's operated with a single pump. There are some ways to do gradient mode, but we'll get into that in a couple of slides. It is a fixed volume dispense, so your separation volume is limited to the volume of that piston, which means you can't generate continual flow. You have to stop and refill that piston, which can cause fluctuations in your baseline. Additionally, it is a pressure-based application. So rather than saying you want to dispense at a certain flow rate, you say you want to dispense at a certain pressure. And so that differs from what sort of we as chromatographers are traditionally used to, which is saying I want to run at a milliliter a minute. In this case, you say you want to run at whatever pressure you apply to that piston head. Now, really what pneumatic pumps are known for, and really where they've kind of gained popularity in the capillary space, is in the process of ultra high or very high pressure chromatography. And so that is due to their ability to do something known as pneumatic amplification. So when you apply that gas pressure to the piston head, you can apply it to a piston head that is a larger cross-sectional area. So in this case, I set it up that we have a 100-to-1 ratio. So the area we're applying gas to has a cross-sectional area 100 times larger than the area that is experiencing the liquid. And what that does is it takes whatever gas pressure that we apply to that cross-section and applies the ratio of those two areas to the liquid. So in this case, because it's 100-to-1, if we were to apply 5 bar of pressure to the outside area, 500 bar of pressure would be generated inside of the system. And so this is primarily used for a lot of ultra high pressure or very high pressure separations where you're using sub 2 micron or sometimes even sub 1 micron particles with meter long columns where you can generate 7,000 bar of back pressure, but you can generate hundreds of thousands of plates in a given separation. It's very easy because you can generate these pressures with only a few bar of gas pressure. And so really that's where this system has gained a lot of notoriety, is through its ability to do pneumatic amplification. Now, primarily it's used with just a single piston. And that limits us because in most applications that we do, we want to be running gradient. And especially one of the major use cases for this is very complex samples where very high efficiencies are needed. And so for those complex samples, gradient elution is a must-have. But when you're only using one pump, the generation of gradients is impossible. So what we do is, and this is a common technique, and there are a number of others, we're not trying to do a full in-depth review, but one common technique is storing a gradient. So by taking, we see here in section A, by taking an external pumping system and flowing a reverse gradient, so starting at very high organic or high elution strength solvent and flowing to a low organic or low elution strength solvent, you can generate a gradient stored in that gradient storage tube. And from there, if you then take that system out of line and put your column, your injector, and your detector in line and start up that pneumatic pump, you're able to generate a gradient with only one pump at those higher pressures without the need to worry about dual pistons or balancing the pumping systems. There have been methods that have used pneumatic pumps for gradient generation. Those so far have primarily been in analytical scale and so, for capillary scale, mainly what we've seen so far has been gradient storage. So what are the pros and cons of pneumatic-based pumps? Well, first and foremost, and really their big claim to fame is they can generate ultra high pressures. Up to 7,000 bar is common. Typically, they use a 1,000-to-1 pneumatic amplification ratio, so you're able to generate these pressures without a ton of need for gas. Additionally, because they don't use motors, it's just gas, you are able to not have as many parts that can break. You don't have to worry about a motor burning out or a gear coming loose or a drivetrain snapping. And so because of that, you can view them as a little bit less maintenance prone. It's not always the case, but you have a reduction in the number of parts that can break. Finally, they're great when using these extremely high efficiency separations because of their ability to do pressure. And so that's really where they've seen a ton of use. Now, the drawbacks, there is significant pulsing during that piston refill. You only have one piston, and when that flow stops or runs out, you have to stop the flow, refill it, and start again. That limits your separation based on the fact that you need to make sure that whatever volume you have stored in that piston, you can complete your entire run within that amount of volume, because otherwise you're going to see a very significant dip within your baseline. Additionally, it's difficult to generate gradients. Not impossible, but it does come with additional steps compared to what we're traditionally used to with a more piston-based system. And again, we aren't able to generate continual flow. It does have to stop. It does have to be restarted. So because of that, it is a drawback. So where is it used? I've mentioned it a million times now. The ultra high pressure separations are key, but it's also great in portable instrumentation, right? All you need is a gas cylinder and a piston head. And so because of that, in isocratic separations, you can use this as a portable pumping system that's very convenient. It's pretty rugged, and it doesn't necessarily have to worry about the same constraints that other types of pumping devices have to worry about. And so that's sort of two of the use cases where it really starts to shine. So next on our list is electrokinetic, or sometimes known as electroosmotic pumps. So similar to the theory of capillary electrophoresis, when you have a buffer system, you'll generate a charged layer around the walls where ions start to migrate. If you then apply an electric field to that, the ions will migrate toward their respective poles, so going toward the negative or the positive. And as those ions migrate, based on the electric field applied, they drag the bulk of solution along with them. And so by doing this, you can generate a flow of bulk solution based on only that little bit of electric field applied. Now, where this really differentiates itself from capillary electrophoresis is that in CE, you apply the electric field across the entire length of your capillary. In electroosmotic or electrokinetic pumping, you apply the field only to the pumping segment and disconnect that field from the rest of the system. So whatever flow you generate moves onward into the system for injection and detection and separation. And by doing that, you can generate capillary scale flows and fairly high pressures completely without the need to apply that voltage all the way across the system. Now, there are a number of methods for inducing this electroosmotic flow and making sure that you can generate reasonable flow rates and relatively high back pressures. Primarily, it has to do with increasing the surface area and the ability to generate that electric double layer. There's a number of different methods. Packed channel, this falls somewhat in line with a column. You pack a number of particles into a tube, and then you can apply the voltage across, and that increases your surface area. So you need less voltage to generate higher flow rates and more pressure. Similar in theory is monolithic. Again, we have monolithic columns in separation mode. You take a porous polymeric substance and stretch it across a length of tubing. And based on that, you can coat it or functionalize it to help with that double layer. And by doing so, you can apply an electric field across it to generate flow. Porous membrane is very similar to the other two. Again, we're just looking to make very porous membranes and surface areas where we can get that flow going. What was really interesting is they also have open channels. So a lot of what I showed initially with just an open tube and ions travel to their respective electron sources. However, what we can do, and what's shown in that picture there, is by taking multiple open channels, you're able to increase your flow by chaining them together in parallel. So if I had a single channel that was capable of producing a nanoliter a minute, and I made 100 of those channels and applied the same voltage to them, now I'm at 100 nanoliters a minute. And so by doing that, you're able to also increase your flow rate and the amount of pressure that you can apply. Now, similar to pneumatic pumping systems, it is a pressure-based system. It's not necessarily a flow rate-based system. But interestingly, you have to be very careful with how you apply these pumps because they are sensitive to shifts in your mobile phase. If you change your buffer strength or your buffer components, if you change the solvent makeup, so you shift the amount of aqueous to organic, each of those impacts its flow rate and it impacts the amount of voltage that needs to be applied. And so when you're working with these systems, every change that you make in the system, you need to validate and make sure that it's actually producing what you think it's going to. So they're very, very useful in the sense that they lack all mechanical parts, right? It's a tube that you apply electricity to. But at the same time, it does come with a number of caveats because you have to be careful about how you apply that electricity to it. They do have methods where you can generate gradients, but they are tricky in the sense that you do have to make sure that across that gradient and across that specific slope, you're translating that voltage properly and ensuring that you can properly generate the flow. Additionally, and this was one that blew my mind when I was researching this, is typically I didn't think of them as capable of producing a lot of high pressure. You know, you're applying voltage to some ionized liquid. How much could it be? But what you're able to do is basically make these in series such that they're all pushing in the same direction. And by doing that, you can generate extremely high pressures. In this case, this one, it was over 1,200 bar of pressure was able to be applied by using a number of these little units of electroosmotic pumps and chaining the first pump into the second into the third, and so on. And so by the time you get to the outlet, you're looking at 1,200 bar of pressure, which is in line with a lot of the other standard mechanisms. And so it was really something pretty impressive to me that was able to be done. So in terms of pros and cons, they are capable of continuous and pulseless flow, right? We're going to get into some of the pulsing flow in a little bit, but in this case, because there's no mechanism, there's no steps, you're able to generate a smooth flow forever, provided you have enough buffer to actually go. There are no moving parts. There's no motors, there's no piston head. And so because of that, these are great in really rugged applications, and we'll get into that. And one thing that's interesting, although maybe not the most applicable to liquid chromatography, is they're capable of bidirectional flow. So flow is generated just because we're applying an electric field to these pumps. If we simply swap the polarity of the field, you could immediately and instantly swap the direction of your flow. And so that's often used in sample handling and less in chromatography, but it is something unique to electroosmotic pumps that I wanted to mention. In terms of the difficulties and the challenges you might face, the flow changes with your mobile phase composition. And so if you change your your buffer concentrations, if you change your organic to aqueous ratio, you have to revalidate and make sure that you're generating the flow or the pressure that you think you are. Gradient generation is often fairly difficult because of this. And it typically requires profiling with each different change. And so because of that, rather than going in and say programming a gradient by saying I want a 5 to 95, you have to program that and then do a number of runs to verify that's actually what you're producing before you can go ahead and use it. Now, where it's useful is portable and extremely rugged applications. What I showed on the left is they're actually using electroosmotic pumps for propellant um, propellant delivery in satellites. And so they were able to go in and make micro thrusters out of these electroosmotic pumps by just applying a voltage across that packed bed and spraying the liquid out. And so it's a extremely robust application because there's no parts that can break. Maybe a wire comes loose, but that's the extent of it. Additionally, they're useful in compact and portable LC. Again, when you're doing method development with these, you have to be careful because, again, the revalidation, but they are incredibly useful if you have a fixed method and you're just trying to apply it in the field. They're rugged and robust, and I mean, they work in space. So they're great for portable applications. Next, moving on, we have something that I think a lot of people are going to be a little bit more familiar with. These are piston-based pumping systems, and these are traditionally what's used in analytical scale. There's two types of pumping systems, although one has become sort of the dominant of the two. So first and foremost, we have a single piston pump where it's just a motor driving a piston head upwards to deliver solvent and drawing it backwards to aspirate solvent back in. And then we have dual piston pumps, which we're going to talk about why they're used, but they allow for a continual flow with limited amount of pulsing, right? In your single pumping setup, you're only able to produce as much as that piston volume is. Then during the refill phase, you have a dip in the baseline similar to pneumatic pumping. With dual pumping, you can offset them in such a way that continuous flow can be generated. So when we're talking about dual piston operation, there's really two primary methods. There's parallel operation and there's serial operation. So with parallel operation, one piston is refilling while the other is dispensing. So it's two pistons at 180 degrees out of phase. And what this lets us do is that as the one finishes its dispense step, the second one is able to draw in solvent, or as the one finishes, the second one drawing in solvent is able to start dispensing. Now, in this case, there is some degree of pulsation, and typically pulse dampeners are used for this. So as the one finishes, there's not a perfect and immediate switch over to the second one, and that can cause some level of dip. To get over that, they have these membranes that allow it to apply some pressure, and during that brief moment, continue to apply that same flow rate. These tend to be difficult in capillary scale because you often are trying to minimize the amount of dead volume or dwell volume that is used in the system. And so in unoptimized systems, I mean, I've seen pulse dampeners that have a milliliter of total solvent internally. And so, you know, if you were running at 1 microliter a minute, well, good luck ever seeing your gradient. You know, we're talking now 1,000 minutes until you actually start to see any of that gradient shift. And so it requires special optimization when you're working on the capillary scale. Another method is serial delivery. And so this is often a bit more complicated and requires careful knowledge of what solvent you're using, its compressibility, and a number of different factors. But in this case, you have two pistons, one sort of a low pressure piston and one a high pressure piston. And what's done is that high pressure piston is used to deliver your solvent to the system, while the low pressure system or the low pressure piston is used to quickly refill that high pressure piston. In this method, you're able to actually reduce the pulsing by a significant amount when compared to parallel, but it does come with the heavy caveat that this is quite difficult to set up and often requires very special knowledge to get working. And so while it's a little more complicated, it's often a little bit better. Now, a lot of you might be saying, well, I have analytical scale pumps in my lab. Why can't I just set my flow rate to 1 microliter a minute and run it? You can, but I wouldn't recommend it because, as I was mentioning before, there's a considerable amount of dwell volume. Your pump head volumes matter. If you have too high a pump head volume, you lose accuracy in your flow rate and you lose stability of your baseline. But it's not impossible to use them for capillary scale as long as you don't care about the amount of solvent you're consuming in general. Instead, what you can do is set the pump up to run at its standard operating flow rate, say a milliliter a minute, and split the flow such that the column and the injector and the detector only experience the flow that you're needed. And so one of the ways to do this is through something known as a T-splitter, which I have shown on screen. In T-splitting, you split the pressure evenly among the two channels. So if you knew that at 1 microliter a minute, your column would generate 1,000 PSI of back pressure. What you would do is you would set up a high flow channel that also generates 1,000 PSI of back pressure at whatever flow rate you're operating at. That way, when you apply that same 1 milliliter a minute to the system, the column experiences its 1,000 PSI and whatever flow rate is required for that. And the high flow takes the remainder of that solvent. So you're able to get steady baselines, rapid gradients. However, you are still using analytical scale volumes. You just are able to still perform those capillary scale separations. T-splitting isn't the only way, and it comes with its own considerations. They have active flow splitters as well, which monitor both sides and help to even out some of that because it's not an exact method, and there can be clogging and differences with mobile phase viscosity that can sometimes throw off your flow rate. Don't necessarily have time to get into that, but there are methods of active flow splitting as well as this, which is a more passive method. So in terms of pros and cons, we are able to generate continual flow, although in this case, it's not pulseless. We have to employ pulse dampeners, which add to our dwell volume. Additionally, we can use existing analytical scale pumps with a flow splitter. So that's great. You don't need to buy additional instrumentation. And these offer flow control. So the other two that we'd previously discussed are typically pressure controlled. In this case, we're able to do flow control. We're able to do gradient generation. I think most of us, if you've used these types of pumps, know it's fairly simple. You plug in what you want and don't think about it. It's pretty simple and straightforward. The downside is typically these pumps come with a large benchtop footprint. Not always, but traditionally that's what we're used to. They require the pulse dampening, and they also require check valves. The more parts that you add to these systems, the more chances you have of failure. When you start to put these check valves into the system, you start to risk needing increased maintenance, increased downtime, and just more areas of risk where you start to introduce failure points. Now, where are these used? Well, first and foremost, benchtop LCs. That's sort of the main use case. For routine assays in a lab, these are sort of the go-to if you want to run the same method a bunch of times or do some experimental R&D. The other place where they're great is high throughput separation. So if you're trying to generate very high flow rates for long periods of time and do injections over and over and over again, these are a great product for that. And in fact, one of the best in terms of their usability, their ability to generate gradients, and their baseline stability. Finally, we're coming back to syringe-based pumping systems, and this is what we here at Axcend use. So syringe-based pumping systems, we typically use either one syringe or dual syringes in a gradient. Pardon me. And you may say these look fairly similar to the piston-based pumps. You'd be right. They are basically the same thing. Really, the only difference is with syringe-based pumps, you operate them with only a single aspiration and dispense step. And so because of that, you are volume limited and you aren't capable of generating continual flow. That typically isn't a problem because you will scale your separation to a volume that fits within inside of these volumes. That being said, it is something to be aware of because as you, well, pardon me. So you draw up solvent, you're able to fill it to whatever volume is needed for your separation, and then you're able to dispense the solvent. And you want to make sure that the solvent amount that you've drawn in is enough to complete your separation. And so really the question then is, why don't I just use a giant syringe, right? If I'm not capable of generating continual flow, but I'm running at 1 microliter a minute, why don't I take a 500 milliliter syringe and then it's effectively the same as continual flow because I can run it forever? The answer is you can't. Typically, syringes have been thought of as pulseless flow in the sense that they don't need pulse dampeners because they don't have that same switchover between the valves. However, syringe pumps don't generate pulseless flow. In fact, they're governed by the steps of the motor that is used to drive that lead screw and drive that piston head in. And so the larger that your syringe volume is, the less steps that motor needs to turn and the less distance that plunger needs to dispense in order to generate flow. And so when you go to these higher volumes, as you can see there in part A, you start to get these distinct pulses in your mobile phase that correlate to the steps on that stepper motor that's driving it forward. And so because of that, you need to be careful with the volume of the syringe that you're using, because if you go to too high a volume, you start to lose flow stability and you start to see very unstable baselines. And so it's key to make sure that you have a syringe with a volume that is appropriate for the separation. You don't want it to be too large and you don't want it to be too small. And so it's a fine line and a careful balancing act in order to keep it all functional. So in terms of the pros and cons, they are considered pulseless in the sense that we don't need a pulse dampener, which helps to reduce our system dwell volume. Additionally, we don't necessarily need check valves, as we'll discuss in a little bit. These also typically are very compact in form factor. They're used in portable instrumentation, as we'll discuss. The downsides are they can't generate continual flow. They do have to refill after emptying, so that does also limit your throughput because you can't just run a sample immediately. You have to stop, refill, and then re-equilibrate before reinjection. And again, if you have mismatched volumes with a low flow rate but a high volume syringe, you're going to start to experience very considerable baseline fluctuations, and you're going to start to see some negative chromatographic performance. So what do we here at Axcend do? So we here at Axcend use a dual syringe based system, one for mobile phase A and one for mobile phase B. This allows us to produce gradient generation exactly like what you're used to on a traditional analytical scale system. Additionally, we don't use check valves. We're able to draw from mobile phase A and mobile phase B, then divert a solvent valve off to the system, which reduces the number of failure points. It makes it a little bit more rugged and reduces the amount of time that's needed to service. It also keeps dwell volume optimized in the sense that we don't have to worry about things like pulse dampeners, the additional check valves. We don't necessarily have to worry about any of that. So it makes for a much more rugged application. We also scale the internal volume of our pumps in order to reduce or in fact eliminate the amount of pulsing that we see from those traditional mismatch in solvent size and stepping. And so this allows us to produce very high quality gradients, very repeatable flow rates, and very stable baselines, all on the capillary scale without some of the drawbacks of other systems. So in conclusion, right, capillary scale LC obviously is going to require some differences in pumping system compared to your analytical scale. For pneumatic pumps, they offer the highest pressures of all of them, sometimes up to 700 bar, but they do require complex setups, especially with gradient generation. Electrokinetic pumps are great for pulseless and continual flow and extremely rugged applications, but they do require revalidation each time you modify the system. Piston pumps, these are what everyone's sort of used to. They are capable of generating continual flow and stable gradients, but they often come with larger footprints and the need for pulse dampeners to reduce some of those fluctuations. And then piston pumps, they can produce, or syringe pumps can produce near pulseless flow in compact form factors, but only for a limited time based on the volume of your syringe. That should say syringe, my apologies. The Axcend Focus LC uses these high pressure syringe pumps, and we're able to produce accurate and repeatable flow in these compact form factors. And so that's sort of a brief overview of the different solvent delivery methods that are available today. Here are my sources, and thank you. We are going to be doing our next one to give a summary of capillary scale columns, differences in packing, commercial availability, all sorts of different aspects. So that'll be coming up soon if you want to check out our website or check out our website for the first installment of the series. And with that, thank you for attending, and I'd love to open the floor for questions. Ooh, I'm in the wrong tab. Pardon me. I was looking at the chat tab. Okay, first question. How does the dead volume of the Focus LC compare to a typical HPLC system from Agilent or Thermo? That's a great question. So if you were to purchase a typical Agilent or Thermo system, I don't know the specific internal dead volumes, but because those are traditionally analytical scale pumps, and I know they have capillary offerings, but traditionally those analytical scale pumps will be leagues higher. If you get down into the capillary scale, I know Thermo has their Neo option. We're looking, ooh, pardon me, we're looking at similar internal dead volumes. I believe ours is maybe a microliter between pumps and column. So it's a very optimized system specifically to keep chromatographic performance as high as possible. Right, we have another question here. How does the Focus LC syringe pump maintain accuracy and repeatability over long runs compared to piston or electrokinetic systems? Are there strategies in place to mitigate syringe volume limitations for extended gradients? Yeah, that's a great question. So we have carefully selected, and I don't necessarily know if I'm allowed to say the actual volumes, but we've carefully selected the volumes of these pumps to mitigate that. And so we're able to operate at these flow rates without fear of those different pulsings. Those tend to occur when you're operating with a milliliter in volume syringe at microliters a minute. And because of that, it's controlled by a stepper motor. And so as that motor does its individual steps, that's when you start to see those pulses. And so that's really what allows us to avoid it. Next question here. What is the advantage of pulseless flow during separation? So with separations, what you don't want to have happen is your flow to stop or to change. If I'm running at a milliliter a minute and all of a sudden my flow drops to half a milliliter a minute and then catches back up really quickly, you're going to notice very considerable shifts and dips on your baseline. It's going to lead to not repeatable results. It's going to lead to poor peak quantification or separation efficiency. And so what we want to make sure is that whatever flow that we're distributing, it remains exactly at that flow rate for the entire duration of the system. You don't want to see those momentary gaps because it's going to start to hurt your chromatographic efficiency. See another question here. Where can we use electrokinetic pumps? So electrokinetic pumps can be used pretty much anywhere. I mean, they use them in satellites. I've seen any number of different applications. They are incredibly useful, but they do come with the caveat that they take a lot of additional testing and validation in order to make sure that you're properly generating the flows and the pressures that you think you are. I see another question here. In my experience, how feasible is it to retrofit existing analytical scale LC systems with flow splitters for capillary applications? Is there anything to be cautious of? Yeah, so when retrofitting these, it's fairly simple, especially if you're doing passive flow splitting with something like a T-splitter. All you have to do, as I mentioned, is make sure that you are able to generate the pressure required by whatever flow rate you want to run at, and then cutting a capillary or a length of tubing or a restrictor that produces a similar pressure at whatever your expected flow rate is. What you have to be careful of is a number of different factors. First and foremost, clogging is a big one. Often the restrictor capillary or that high flow capillary is something with a little bit of a smaller inner diameter to generate the same pressure as a column. Because of that, you can run into issues where if a particulate gets in and clogs that, all of a sudden now the pressure is 100% going to your capillary and you're sending a milliliter a minute into a column that probably only needs 10 microliters a minute. And so something's going to blow, a fitting, the column. I've had it happen. It's not great, and it's typically very violent in how quickly it breaks. The other factor is when you're doing something like a gradient separation, if there's a mismatch in volumes between your high flow and your low flow, the gradient will clear that high flow system before it clears the low flow system. And then what you're seeing is different viscosities between the two flow paths. And so that can lead to momentary fluctuations in terms of flow and in terms of the split ratio. I see another question here. What considerations should be taken into account when choosing between pneumatic and electrokinetic pumps for a portable or field deployable LC system? Yeah, that's a great question. So I think primarily what you want to be aware of is you need to know how available different aspects will be. So let's take an extreme example, the electrokinetic pumps in space, right? That's a great application because all you have to do is apply voltage. If you were to use something like a pneumatic pump in space, you have to be aware of the fact that you're applying a gas pressure to it. And so any of that gas needs to be taken up, it needs to be available, and it needs to be something that is accessible. And so when you're looking at a field deployable system, you want to look at the application and making sure that one, the pumps are capable of delivering an appropriate flow and an appropriate pressure, but also that you're selecting a pump that is serviceable and can be used long term out in the field without some of those drawbacks. Another question here. I mentioned that electrokinetic pumps offer pulseless flow. Are they trade-offs in terms of pressure stability, solvent compatibility at these high back pressures? Not particularly. I mean, you want to make sure there is a buffered system so you have those ions available to form the double layer. That being said, pressure stability, it is a constant pressure system. So whatever pressure you are applying is directly dependent on your mobile phase, the voltage applied, and the porosity and the efficiency of that electrokinetic pump, whatever sort of membrane option that you choose. That being said, you can use similar solvents and while pneumatic pumps can typically generate higher pressures, those are pressure fixed applications, and so they often lead to very similar options. All right. Don't necessarily see any more questions in the chat. So with that, I think we will call it here. Thank you everyone for attending. Please make sure to tune in next time for our series on capillary scale columns. And if you missed the first one, make sure to check us out at axcendcorp.com. And if we didn't get to your question here today, feel free to reach out to us. I'd be happy to answer. And if you wanted us to go more in depth in something or still had questions, please feel free to reach out and we can discuss that as well. With that, thank you all for coming, and we'll see you next time.